while Andromeda is a staggering 2.5 million light-years away. The sheer scale of interstellar distances is something that our human brains, accustomed to terrestrial measurements, struggle to truly grasp. To even begin to comprehend such a journey, we must first understand the units astronomers use to measure the cosmos, and then attempt to contextualize these almost unfathomable distances. Our everyday lives are governed by meters and kilometers, or miles if you prefer. We measure the distance to the grocery store, the length of a road trip, or the circumference of the Earth in these familiar terms. But these units become utterly impractical when we venture beyond our planet. Even within our own solar system, the numbers quickly become astronomical, quite literally. For instance, the average distance between the Earth and the Sun is approximately 150 million kilometers, or 93 million miles. To simplify these immense figures, astronomers use the astronomical unit, or AU. 1 AU is defined as this average Earth-Sun distance. So, instead of saying Neptune is about 4.5 billion kilometers from the Sun, we can say it's roughly 30 AU away. This makes distances within our solar system much more manageable to discuss and compare. However, even the AU falls short when we consider the vast emptiness between stars. Our solar system itself, out to Neptune, spans about 60 AU, but it doesn't end there. Beyond Neptune lies the Kuiper Belt, extending to about 50 AU, and then the Oort cloud, a theoretical spherical shell of icy bodies that surrounds our solar system. The inner edge of the Oort cloud is thought to be between 2,000 and 5,000 AU from the Sun, with its outer edge potentially reaching as far as 100,000 to 200,000 AU. To put this into perspective, if the Earth were a marble, the Oort cloud would be a sphere several kilometers across. Even Voyager 1, our most distant spacecraft, launched in 1977 and traveling at approximately 17 kilometers per second, has only just begun to exit the heliosphere, the protective bubble of solar wind and magnetic fields surrounding our solar system, and entered interstellar space. It will take Voyager 1 about 300 years to reach the inner edge of the Oort cloud and possibly 30,000 years to fly beyond its outer edge. To measure the truly immense gulfs between stars and galaxies, we introduce the light year. A light year is not a unit of time, as its name might suggest, but a unit of distance. Specifically, the distance that light travels in a vacuum in 1 Earth year. And light, as we know, is incredibly fast. In a vacuum, it travels at precisely 299,792.458 kilometers per second, or about 186,000 miles per second. This means that in a single year, light covers an astonishing 9.46 trillion kilometers, or approximately 5.88 trillion miles. Let's put that into context. Light from the moon reaches us in about 1.3 seconds. Sunlight takes approximately 8 minutes and 20 seconds to travel the 150 million kilometers to Earth. Even within our solar system, light travel times quickly add up. A trip at light speed to the very edge of our solar system, the farthest reaches of the Oort cloud, would take about 1.87 years. Now, consider our nearest stellar neighbor, Proxima Centauri, a red dwarf star that is part of the Alpha Centauri system. It's located about 4.25 light-years away from us. This means that the light we see from Proxima Centauri today left that star over 4 years ago. If an airline offered a flight there by jet, it would take 5 million years. Even at the speed of Voyager 1, a journey to Proxima Centauri would take over 70,000 years. This is why Proxima Centauri, despite being our closest stellar neighbor, still appears as a mere point of light, invisible to the naked eye. Our own Milky Way galaxy is a vast spiral, estimated to be around 100,000 to 180,000 light-years in diameter. The center of our galaxy is about 26,000 light-years away. And then we come to Andromeda, our galactic neighbor, a stunning 2.5 million light-years distant. This means that when we gaze upon the Andromeda galaxy, we are seeing it as it appeared 2.5 million years ago. Imagine, the light that is reaching our eyes tonight began its journey through the cosmos when early hominids were just beginning to walk the Earth. The observable universe, the portion of the universe from which light has had time to reach us since the Big Bang, has an estimated radius of about 46.5 billion light-years, making its diameter approximately 93 billion light-years. These numbers are so immense that they almost lose all meaning. They highlight the incredible emptiness of space and the truly daunting challenge of interstellar, let alone intergalactic, travel. The distances are not just large, they are mind-bogglingly, profoundly vast. It's against this backdrop of cosmic immensity that the principles of special relativity become not just theoretical curiosities, but crucial considerations for any hypothetical journey across the stars. The vastness of space, as we've established, presents an almost insurmountable barrier to conventional travel. But what if our understanding of space and time itself is incomplete when confronted with such extreme scales? This is precisely where Albert Einstein's theory of special relativity enters the picture, fundamentally reshaping our cosmic perspective and offering both profound challenges and unexpected possibilities for interstellar voyaging. Published in 1905, Einstein's special relativity is built upon two deceptively simple, yet revolutionary, postulates. The first states that the laws of physics are the same for all observers in uniform motion, meaning those moving at a constant velocity in a straight line. This is known as an inertial frame of reference. Whether you're conducting an experiment in a stationary laboratory or on a spaceship cruising smoothly through the void at 1,000 kilometers per second, the fundamental laws governing the universe, from electromagnetism to mechanics, will yield identical results. This principle, inherited in part from Galileo, implies there's no absolute state of rest or motion. All motion is relative. The second postulate is where things get truly mind-bending. The speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer. This constant, denoted by c, is approximately 299,792,458 meters per second, or about 300,000 kilometers per second. Think about that for a moment. If you're standing still and shine a flashlight, the light travels away from you at c. If you're hurtling through space at half the speed of light, and then shine that same flashlight in your direction of travel, the light still moves away from you at c. This defies our everyday intuition, where we'd expect to add our speed to the speed of the light. This constancy of light's speed, however, has been rigorously confirmed by experiments, most famously by the Michelson-Morley experiment in the late 19th century. These two postulates, when taken together, lead to some truly extraordinary consequences for space and time. Consequences that are not merely theoretical quirks, but observed realities at high velocities. One of the most famous of these is time dilation. Imagine a light clock where a photon bounces between two mirrors. For an observer at rest relative to this clock, the photon travels a direct path up and down. Now, imagine this clock is moving horizontally at a very high speed. For a stationary observer watching the moving clock, the photon now has to travel a longer, diagonal path to hit the mirrors because the mirrors themselves are moving. Since the speed of light is constant for all observers, and the photon in the moving clock has a greater distance to cover, it must take longer for it to complete a bounce. Therefore, the moving clock appears to run slower than a stationary one. This means that time itself is not absolute. It passes differently for observers in relative motion. The faster an object moves, the slower time passes for it relative to a stationary observer. This effect becomes significant at speeds approaching a substantial fraction of the speed of light. Hand in hand with time dilation is length contraction. Just as time intervals are affected by relative motion, so are spatial dimensions. An object moving at a relativistic speed will appear shorter in the direction of its motion to a stationary observer. The length of the object is maximized when measured in its own rest frame. So, a spaceship traveling at near-light speed would appear compressed in its direction of travel to an outside observer. From the perspective of the travelers inside the ship, however, everything would seem normal and the distance to their destination would appear shorter. Another profound consequence is the relativity of simultaneity. This concept dictates that two events that appear to happen at the same time for one observer may not be simultaneous for another observer who is in relative motion. There is no absolute now that all observers agree upon across vast distances. This challenges our intuitive understanding of a universal, synchronized timeline. These effects, time dilation, length contraction, and the relativity of simultaneity, are all mathematically described by the Lorentz transformations, a set of equations that relate the coordinates of space and time between different inertial frames of reference. These transformations show how space and time are inextricably linked, forming a four-dimensional continuum known as spacetime. Finally, special relativity also gives us arguably the most famous equation in all of physics, E equals mc squared. This equation reveals the profound equivalence between mass and energy, demonstrating that they are interchangeable. A small amount of mass can be converted into an enormous amount of energy because the speed of light squared, c superscript 2, is such a large number. This principle underlies nuclear reactions, like those powering stars and nuclear weapons. It also implies that as an object approaches the speed of light, its observed mass increases, requiring an infinite amount of energy to reach c. This is why, according to special relativity, nothing with mass can ever truly reach or exceed the speed of light. The speed of light acts as the ultimate cosmic speed limit. These principles of special relativity, while seemingly counterintuitive, are not mere theoretical constructs. They are experimentally verified and form the bedrock of modern physics, playing a crucial role in technologies like GPS systems, which must account for relativistic effects to maintain accuracy. For interstellar travel, special relativity tells us that while faster-than-light travel is impossible, journeys at near-light speeds would have profound effects on the perception of time and distance, making incredibly long voyages feel much shorter for the travelers themselves, even as millennia pass back on their home world. This fascinating consequence of special relativity, known as time dilation, dictates that time is not absolute, but rather relative to an observer's motion. For a traveler journeying at speeds approaching that of light, time would literally slow down relative to someone remaining on Earth. This isn't just a theoretical quirk, it's a fundamental aspect of how our universe operates, and it has profound implications for interstellar travel. Imagine a spaceship accelerating to 99% of the speed of light. For the astronauts on board, their clocks, their biological processes, and their very perception of time would continue as normal. They wouldn't feel time slowing down. A minute would still feel like a minute, an hour like an hour. However, to an observer back on Earth, watching the spaceship speed away, the clocks on board that vessel would appear to tick more slowly. The astronauts would seem to be moving in slow motion, as if wading through treacle. The mathematics behind this phenomenon are precise. The faster an object moves, the greater the time dilation. At 10% of the speed of light, time runs only about 0.5% slower. But as speeds climb, the effect becomes exponential. At 90% of the speed of light, time runs approximately 2.3 times slower. Push that to 99% of the speed of light, and time slows by a factor of about 7. If a spaceship were to travel at 99.999% of the speed of light, 1 year for the travelers would correspond to 224 years on Earth. This means that a journey of, say, 50 light years, which would take 50 years at the speed of light from an earthbound perspective, could feel like only a few years for the astronauts themselves if they travel close enough to light speed. This isn't an illusion or a trick of perception. It's a genuine difference in the passage of time. When the astronauts return to Earth, they would indeed be younger than their earthbound counterparts who have experienced a greater passage of time. This effect has been repeatedly confirmed by experiments, from observing the extended lifetimes of unstable subatomic particles in particle accelerators to the minuscule but measurable differences in atomic clocks flown on airplanes compared to those on the ground. Even astronauts on the International Space Station, orbiting Earth at about 27,500 kilometers per hour, experience a slight time dilation, aging a few milliseconds less than people on Earth over a 6-month period. While this difference is negligible in our daily lives, it's a direct confirmation of Einstein's theory. The concept of time dilation also extends to gravity, a phenomenon known as gravitational time dilation. The closer one is to a massive object, the slower time passes. This is why clocks at higher altitudes tick slightly faster than those at sea level, and it's a crucial factor that needs to be accounted for in GPS satellite systems to maintain accuracy. In extreme cases, like near a supermassive black hole, time dilation can be immense. The film Interstellar famously depicted a planet orbiting a black hole where 1 hour on the planet was equivalent to 7 years on Earth due to extreme gravitational time dilation. While the exact parameters of that planet might be unphysical, the underlying principle is scientifically sound. For interstellar travel, this means that while the vast distances remain a challenge, time dilation offers a peculiar advantage to the travelers. A journey that would span generations for those left behind could be completed within a single human lifetime for the crew on a relativistic spacecraft. They would effectively be traveling into Earth's future. This has profound implications for communication, as messages sent from Earth would take years to reach the ship, and replies would take even longer, with the time gap increasing due to time dilation. Eventually, communication could become a one-way street, with signals from Earth potentially never reaching a constantly accelerating ship. However, the human body itself faces significant challenges during prolonged space travel, even with time dilation making the journey feel shorter. Microgravity leads to muscle atrophy and bone degeneration, and astronauts experience changes in their cardiovascular system, eyesight, and immune system. Radiation exposure also poses a serious long-term health risk. So, while time dilation might shorten the subjective duration of an interstellar voyage, the physiological demands on the human body remain immense and require innovative solutions. The thought experiment known as the twin paradox provides a compelling, if initially perplexing, illustration of time dilation and its implications for interstellar travel. Imagine two identical twins. One, let's call her the space twin, embarks on a journey aboard a high-speed rocket, traveling at a significant fraction of the speed of light, while the other, the Earth twin, remains at home. When the space twin returns, she will have aged less than her earthbound sibling. This isn't a trick or a contradiction, but a direct consequence of special relativity. The paradoxical aspect arises from a seemingly symmetrical viewpoint. Couldn't the space twin argue that she was stationary and the Earth twin was moving, and therefore the Earth twin should be younger? However, the key to resolving this apparent contradiction lies in the asymmetry of their journeys. The Earth twin remains in a single inertial frame of reference, meaning they experience no acceleration. The space twin, on the other hand, undergoes acceleration when she departs, decelerates to turn around, and then accelerates again to return to Earth. These changes in velocity mean the space twin is not always in an inertial frame of reference. This acceleration is what breaks the symmetry and leads to the measurable difference in aging. To put it simply, the traveling twin's trajectory involves switching between different inertial frames, which is not the case for the twin who stays on Earth. This fundamental difference means their experiences of time are not equivalent. The concept has been experimentally confirmed, not with human twins, but with atomic clocks and even elementary particles in accelerators, where their inner clocks run slower when they travel at relativistic speeds. Consider a hypothetical journey to a star system 4.24 light-years away, like Proxima Centauri. If a spacecraft could travel at 90% the speed of light, an outside observer on Earth would measure the journey as taking approximately 4.7 Earth years. However, due to time dilation, the astronauts on board would experience only about 2 years. This means that while 4.7 years would pass for those on Earth, the astronauts would only age by 2 years. The implications for longer journeys are even more dramatic. If a spaceship could continuously accelerate at 1 g, an acceleration comfortable for humans, it could reach almost anywhere in our galaxy and return to Earth within 40 years of ship time. However, tens of thousands of years would have passed on Earth during that same period. For instance, traveling to the center of the Milky Way, approximately 30,000 light-years away, and returning would take about 40 years for the astronauts, but over 60,000 years would have elapsed on Earth. This disparity in experience time is the core of the twin paradox and a central consideration for interstellar travel. While it offers the tantalizing prospect of relatively short subjective travel times for astronauts, the objective reality for those left behind is vastly different. A journey to the Andromeda galaxy, for example, which is about 2.5 million light-years away, would take approximately 2.5 million years as observed from Earth, even if traveling at the speed of light. However, for a traveler moving at an extremely high percentage of the speed of light, the journey could subjectively be much shorter, even as little as a year. Upon their return, billions of years could have passed on Earth, and human civilization as they knew it would likely be long gone. Beyond the relativistic effects, the human body faces immense physiological challenges during prolonged space travel, regardless of time dilation. Microgravity, for instance, leads to significant muscle atrophy and bone density loss, particularly in weight-bearing bones like the femur and spine, with astronauts losing 1.5 to 2% of bone density per month. Muscle mass can decline by 20 to 30% during 6-month missions. The cardiovascular system also undergoes deconditioning, with fluid redistribution, decreased blood volume, and a reduction in heart size and function. These changes can lead to orthostatic intolerance or dizziness upon standing when returning to a gravitational environment. Furthermore, long-duration missions can impact the brain. Studies have shown that the brain's ventricles, fluid-filled cavities, expand significantly in astronauts who complete missions of at least 6 months, and it can take up to 3 years for these ventricles to fully recover. This fluid shift can push the brain higher within the skull, and the long-term consequences are still being investigated. The immune system can also be compromised, increasing the risk of infection. The risk of radiation exposure remains a critical concern for deep space missions. Beyond Earth's protective magnetic field, astronauts are exposed to high-energy, heavy ions and protons from galactic cosmic rays and solar particle events. This radiation can damage DNA, increasing the lifetime risk of cancer, and has been linked to cardiovascular disease, central nervous system effects, and even accelerated aging. A 3-year mission to Mars, for example, could expose astronauts to radiation doses exceeding 1,000 MSV, a level at which the risk of cancer is well documented. Shielding is essential, but completely mitigating these risks is a significant challenge. Therefore, while time dilation offers a fascinating theoretical solution to the immense temporal scales of interstellar journeys from the perspective of the traveler, the practical realities of human physiology and the harsh environment of space present formidable obstacles that demand innovative solutions before such voyages can become a reality. The immense scale of interstellar distances and the profound implications of special relativity, particularly time dilation, paint a compelling, albeit challenging, picture for the future of interstellar exploration. While the theoretical framework allows for journeys to distant stars within a human lifetime from the traveler's perspective, the practical hurdles remain formidable. Yet, the allure of other galaxies, especially our closest major galactic neighbor, Andromeda, continues to drive scientific inquiry and fuel our aspirations for future exploration. The Andromeda Galaxy, also known as Messier 31 or M31, is a barred spiral galaxy, much like our own Milky Way. It's the largest galaxy in our local group, a cluster of over 40 galaxies, and is estimated to contain about 1 trillion stars, compared to the Milky Way's 200 to 400 billion. Andromeda is a truly colossal structure, with a diameter of approximately 152,000 to 220,000 light-years. It's also remarkably close, at a mere 2.5 million light-years from Earth, making it one of the few galaxies visible to the naked eye as a faint smudge of light in the night sky. This proximity is particularly significant because Andromeda is currently hurtling towards the Milky Way at a speed of about 110 kilometers per second, 68 miles per second, or roughly 250,000 miles per hour. This means that in about 4 to 5 billion years, our two galaxies are expected to collide and merge, eventually forming a larger elliptical galaxy, sometimes playfully nicknamed Milkdromeda. While the idea of a galactic collision might sound catastrophic, the vast distances between stars mean that individual stellar collisions are highly improbable. Our solar system will likely survive, though its position within the newly formed galaxy could shift dramatically, and the night sky would be transformed with a spectacular display of new star formation. The prospect of Andromeda's eventual merger with the Milky Way raises fascinating questions about future exploration. If humanity were to survive and thrive for billions of years, perhaps even developing technologies to traverse the vast interstellar distances, Andromeda would become not just a destination, but our inevitable cosmic home. However, reaching Andromeda with current or even foreseeable technology presents immense challenges. Even at speeds approaching that of light, the journey would take approximately 2.5 million years from an Earthbound observer's perspective. While time dilation would shorten this subjective travel time for the crew, perhaps to a few years or even just over a year if traveling extremely close to the speed of light, the objective time elapsed for those left behind would still be millions of years. This means any such journey would inherently be a one-way trip into the far future for the travelers. The implications for future exploration extend beyond just reaching Andromeda. The journey itself would necessitate revolutionary advancements in propulsion, life support, and human physiology. Interstellar travel is not feasible with current propulsion technologies, requiring enormous amounts of energy to reach a significant fraction of the speed of light. Concepts like antimatter rockets, which could theoretically achieve 50% or even more of the speed of light by harnessing the immense energy released from matter-antimatter annihilation, are still highly theoretical. Even more speculative are ideas like warp drives or wormholes, which would bend space-time to circumvent vast distances, but these remain firmly in the realm of science fiction, requiring exotic matter and energy levels far beyond our current capabilities. Beyond propulsion, the human element poses significant obstacles. Prolonged exposure to the harsh space environment, including microgravity and high-energy radiation, causes profound physiological and psychological changes. Astronauts experience bone density loss, muscle atrophy, cardiovascular deconditioning, immune dysregulation, and neurocognitive and psychological stress. While countermeasures like exercise regimens and fluid loading have shown some efficacy for missions within our solar system, Long-duration interstellar voyages would demand far more robust solutions, perhaps even fundamental biological modifications or advancements in artificial intelligence to manage and maintain human health over generations. The concept of generation ships, colossal spacecraft designed to house thousands or even millions of human beings for thousands or millions of years, represents one theoretical solution to the immense temporal scales. Within such a vessel, generations would be born, live, and die, never knowing a home other than the ship itself, a self-sufficient world traveling through the void. This presents not only technical challenges in creating closed-loop ecosystems and robust infrastructure, but also profound social and cultural considerations. What kind of societies would emerge in such isolated, multi-generational environments? How would their understanding of humanity and their purpose evolve across millennia of travel? The ultimate goal of such exploration could be the search for extraterrestrial life and the potential for colonization. Given Andromeda's immense size and star count, estimated to be 2 to 3 times that of the Milky Way, the probability of finding habitable planets and even intelligent life, there is a tantalizing possibility. While no definitive evidence of life beyond Earth has been found, the sheer number of stars and potential planets in Andromeda suggests a high likelihood of life flourishing in various forms. However, even if such life exists, detecting it from our current vantage point is incredibly difficult, and any signals we receive would be millions of years old. The journey to Andromeda, whether physical or observational, represents the ultimate frontier of human exploration. It challenges our technological limits, our understanding of physics, and even our definition of what it means to be human. While a direct, crewed mission to Andromeda remains a distant dream, the scientific pursuit of understanding this majestic galaxy continues to inform our knowledge of galactic evolution, the potential for life beyond Earth, and our own place in the vast, expanding universe. The implications for future exploration are not just about reaching a destination. They are about the transformative journey of discovery itself, pushing the boundaries of what we believe is possible and perhaps, in the process, redefining our destiny among the stars.